Hello, my name is Anthony Stempt, and this is Physics 2, Lab 4. In this presentation, I'm going to give an introduction of this week's lab, then I'm going to go into some specifics on the procedure of this week's experiment, and then go into a discussion of some possible areas of error and the what-if questions for this lab. So in this lab, we wanted to predict the behavior of circuits containing resistors in a series and in parallel, use multimeters to measure the actual values of conventional current and potential difference in circuits, then examine the behavior of ohmic resistors and capacitors. The values that I calculated in this experiment match very well to the theoretical values that you'd get from using equations with a reasonable margin of error. Some important concepts for this lab is going to be the conservation of energy as it applies to series currents, the loop and node rule for circuits, Ohm's law, a general understanding of RC circuits, specifically their time dependence, and the potential components of a circuit, so ammeters, batteries, capacitors, resistors, and voltmeters, and then what they do. So the important equations kind of go back to those important physics concepts. You have loop rule, node rule, Ohm's law, potential difference of a capacitor, capacitance, and RC, which was given in the lab handout. These equations are used throughout the experiment. So the first step of the experiment was to set up a simple circuit that you see on the right-hand side with those specific values that are labeled. And then I found that both ammeters, ammeter 1 and 2, measured a current of 0.02 amps. That's important later. Next, I removed one of those ammeters, ammeter 2, and added a voltmeter. So why we're reading a current of 0 in this situation is because no current is traveling through that voltmeter. There's a lot of resistance going on in the voltmeter, which results in no effect on the circuit itself. And since it's not an open circuit, we have no current and then no amps. Our predicted amp value is going to, using the voltmeter, if that second ammeter were still there, is going to be 0.0204 amps. Experimentally, we found that to be a little bit different, and that was about a 2% error, so that's pretty reasonable. Then I used the voltmeter to calculate some potential differences at prescribed points throughout the experiment. So from the two sides of the battery, we get a potential difference of 3 volts, which makes sense because there's 3 volts coming from the two batteries. And then on the right-hand side with the resistors, I get a net voltage of negative 3 volts. And per the loop rule, the potential differences of a circuit need to sum to 0, which they do in this case, and this circuit satisfies the loop rule. So when I observed this in parallel with an ammeter on the 100 ohm resistor, the current increased from 0.02 amps to 0.06 amps. Then I went on to calculate the resistance of certain parts of this circuit. So the 47 ohm resistor measured at 48 ohms actually, which is a 2.13% error. The 100 ohm resistor got a resistance of 102 ohms, and then the wire and ammeter both had a resistance of 0, which maybe isn't true in the real world, but in this simulation it is. So for the RC circuit, which is set up on the right-hand side, I had a light of 2 different resistances, and I measured the time that it took to charge the light from the battery, which is that brightening step, then how much time it took for that energy to discharge, which is the dimming until the current decreases to 0 over time. So there's that time dependence. Those 2 data sets of times just reflect those experiments that I ran. Finally, I had a bigger kind of setup where I measured the time dependence across a discharging capacitor in this fashion, and I used this equation here that was given in the lab handout. So on this slide, I'm going to go into some more examination of that data. Using the slope from that line of best fit on the last slide, I calculated that the RC value was at 5.63 seconds, whereas using the equations given listed on that beginning slide, I found that it took about 6 seconds, which is a 6% error, give or take. So some error analysis, the most prone areas to error are going to be the timed portions because that's some human error. So the areas that require you to time and precisely calculate the voltage or record the voltage is what resulted in that 6% error that I saw on the last slide. So some what ifs. If this were happening in real life and I used a real ammeter rather than the simulated one, Well, it would be I would get lower current values because there's going to be some more resistances going on that I couldn't account for in this simulation, and then there's just going to be wear and tear on the equipment, general inaccuracies. Again, if I was using a real battery to charge a real capacitor with no resistor in the circuit, I would also see a difference because the wires and the batteries and the ammeters in real life are going to have some resistance. So those values would be skewed. Likely they would be lower. All right, that's all I have, and thank you for watching.